Log on, tune in, find out. Another good idea from Cambridge.
I want to talk about. Let me just say a few words about the meaning of this two terms, mean-driven and coalescence or coagulation. So from, let's say, a physical point of view, coalescence or coagulation is the generic mechanism by which particles that collide and merge together, they increase their size. So as a consequence of collision and merging. So probably one of the most famous coagulation equation is the one which was derived in 1916 by the Polish physicist Marian Smolowski. And the elementary reactions, which is modeled by this Smolowski equation, is a binary reaction that you take a particle which has a size x, a size or a volume x being either a positive real number or an integer if you normalize, let's say, some minimal volume to be 1. Then two of these particles meet, one of volume x and one of volume x star, and after their meeting they form a new particle, so a single particle with volume x plus x star. So you have conservation of volume during this elementary reaction. And these reactions occur with a rate k of x star, which depends on both x and x star in principle. Of course, it could be constant also. What is, I would say, important in this elementary reaction is that somehow all particles are similarly involved in the reactions. I mean, of course, they are, because the reaction rate depends on the respective volume of the incoming particles. The reaction, the reaction rate, the likeliness of coagulation of two particles depend on their volume, but in principle, the reactions are the same for all particles. This is not always the case, and there is a, let's say, a sub-model of the Smolowski equation, which is either called the addition model or the Baker-Döring model, but without fragmentation, where in that case the volume of a particle is assumed to be a positive integer, and the only reactions which is taken into account is the growth of particles by the addition of let's say, an elementary particle, meaning that the only reactions which are taken into account is that a particle of volume x coagulate with a particle of volume 1 to give a particle of volume x plus 1. So in this model, and of course, again, the rate k of x of this reaction depend on the volume of the incoming particle. And in this model, you have a specific role of the particles with the minimal volume, which is here equal to 1. So this allows me somehow to come to the second word, which was in my title. Mean-driven is going to mean a coagulation equation, a coagulation model, in which somehow the particle of minimal volume play a different role than the other ones. So this is the case already in this addition model, but in this addition model one can prove that the minimal volume here is always x equal 1, of course provided you have initially particle of size or volume 1. So there are several possibilities to have a so-called mean-driven coalescence model. Probably maybe one of the oldest one is so-called the interval coalescence, where you consider the real line with a partition of intervals, and at each step, or at some instant of time, you take the smallest interval, the smallest with respect to its length, or if there are several, you choose one of them. you take his right neighbor and his left neighbor and you glue them together in order to form a larger interval in that sense. So you can also think of, let's say, a variant of this model in that instead of having some interval on the line for which you have somehow a kind of an order, then what you can think is that, that you have particles. You take one of the particles with the smallest size, you take at random two of the particles and you glue them together in order to form a new particle. And in fact, you can somehow generalize this kind of dynamics. So at each step of your evolution, so if L is the minimal volume, meaning that it's the volume of the smallest particle present in your distribution, in your system of particle, you choose an integer k with a probability pk, and you choose k of a particle in your system with uniform probability, and you glue them together and they form a new particle which has as a volume the sum of the volume of the previous of the incoming particles. And you can write some evolution equation for some mean field evolution equation for this system, and they have been studied by Gale-Milke and Menon-Nittamer.
But in the second case, you don't have a geometric structure.
No, here you have no geometric structure. In that one you have one, yes, but not in that one. So you. There is another way of in fact, what is important in these models here compared to the previously mentioned Baker-Doring model or addition model is that the minimal volume L is changing with time in that particular case. Another class of mean-driven coalescence equations has been derived by Derrida, Godrèche, and Nicoutieli, and roughly speaking, it's the following. You take a positive integer k, and at each step of your evolution, if L denotes again the minimal volume of the particles in your distribution, you take a particle with this smallest volume, you break it into k equal pieces, or if k equal 1, you do not break it at all, and then you choose k of a particle at random with uniform probability, and you glue each pieces to one of these k particle here. So in the original paper by Derrida, Godrèche, and Nicoutieli, k is either 1 or 2. But you can extend it to, and so somehow in that model you have, let's say, some kind of fragmentation first of the smaller particle, and then a coagulation event. But you consider it all at once. And again here, what you can see is that there is a temporal relation of the minimal volume. So what I would be interested in this talk is actually one particular case of this model, where we forget this step, and in fact where we choose that k is equal to 1 always, so that at each step of the evolution, if L is throughout the talk is still the minimal volume of my system of particle, then at each step of my evolution, I take one of the particles of smallest volume, another particle, and I join them together to obtain a larger particle. And of course, because L is the smallest volume in the system of particle, X here will also be bigger than L. So here I have at least a particle with volume 2L. And so, as in the model by Derrida, Godrèche, and Nicoutieli, so Px is chosen with uniform probability. And somehow, in order to complicate a bit the game, what we propose is to take exactly into account the same reaction, but choosing the particle Px, to which we are gluing our smallest particle, choosing it with an a priori constant rate which depend on both the minimal volume and x. And this is what I want to talk about now. However, from the very beginning, I will make a basic assumption, which will be valid throughout my talk, is that I'm considering the case where the volumes only ranges in the set of positive integers. So, well, what I will first speak about is given this picture, how to construct a stochastic model for this evolution and a deterministic model. Then I will show that these two models are related one to another, and that actually the deterministic model is the hydrodynamical limit of the stochastic process. And in the end, I will comment about the evolution with time of the minimal volume. So just to start with a, well, very briefly and very roughly, because I'm not a probabilist, so just to avoid to say wrong things, a very short account of how is the evolution of a stochastic process. So one starts from a system of particles where in fact we describe x, which is xi, is in fact a sequence of integers, where xi is simply the number of particles of volume I bigger than 1, which we have in our system of particles. So the minimal volume of x is simply the smallest index for which xi is positive. So what I do at each step of the evolution of this, during one step of the evolution, is I choose, so I compute the minimal volume. I choose one particle of volume Lx, another particle of volume J, bigger or equal to Lx, and then the new state Y of my system of particle is the following. So I remove one particle of minimal volume, I remove one particle of volume J, and I had one particle of volume Lx plus J. So this is, of course, if J is bigger than the minimal volume, while if the J chosen here is exactly the minimal volume, then I will lose two particles of minimal volume and gain one particle of volume 2Lx. And of course, the other classes of particle remain unchanged, and so they do not move, but they stay as they are. So this is one elementary, let's say, step. Now to have a time-dependent process, so we start again with an initial state, which is again xi initial is the number of, is an integer and is the number of particles of size of volume I we have initially. And then at each, well, from time to time, we jump from one state to another one according to the previous rule. And the rate of this jump is computed as a function indicated here. An important point on this in this business is that if you if we just come back here, is that in both the state, if you start from one state and the two next state, in fact, if you compute, they have exactly the same total volume as the previous one, so that throughout this process you have conservation of total volume, meaning that if you start with initial data which has a total volume equal to m, then this property stays true for during the time evolution. Let me now go to the deterministic model. So in that case, I introduce x of t to be xi of t, where now xi of t is not an integer and is the density of particles of volume I bigger than 1 and time t. So again, I define the minimal volume at time t, which is simply the minimum of the i's for which xi of t is strictly positive. then as long as this minimal volume is equal to I, then of course, because L of t is the minimum, I have nothing I have no particles of size smaller than I minus 1. The particles of size I, they disappear because they, of size I, which is here the minimal size, they disappear as a consequence of coalescence with larger particles, or with particle also of the minimal size. And all the other particles with size are strictly larger than the minimal size, but they disappear because they coalesce with particle of minimal size and form a larger particle, and they are formed when a particle of size j minus I meet a particle of minimal size and gives this. So an interesting feature of this system here is that it is linear, as is quite clear from there. However, it is linear as long as the minimal volume does not change, because then as soon as you will have a jump of minimal volume, then you have to change the ordinary, the system of ordinary differential equation. And so somehow this is a piecewise linear system of ordinary differential equation. So if I write it, let's say, introducing this Bj, this right hand side, in order to have a more compact form, I can also check that there is total volume conservation, at least formally, on this set of ODE, and one can prove the following. Well, one can prove and study the well-posedness under the following assumptions. So concerning this kernel here, which is a coagulation kernel, which describes the likeliness that a particle of volume J will wish to merge with a particle of volume I. So this is a classical assumption that it does not increase faster than I times J. And I assume also that the infimum of this is positive. This is to avoid some, let's say, degenerate situation which would complicate the analysis. And I take an initial data which is a positive for first component. So I have the minimal volume initially is 1, and then all the other initial data are positive, and the total volume is equal to 1. So once you have this, what you can prove for the deterministic system is that there is a unique pair L and X, such that x of 0 is the initial data. Then there is an increasing sequence of times with t0 equals 0, and in fact the function L of t here, which is going to be the minimal volume, is constant and equal to I on this interval ti minus 1 ti. And then I define t infinity as the supremum of the ti here. Note that, in fact, this t infinity is not given a priori, because, there is an increasing sequence, but it increases to t infinity, but it's unclear yet what is this t infinity. For any time between 0 and t infinity, so xj of t is 0 if if j is smaller than L of t, and xl of t at time t is positive. So meaning exactly that L of t is the minimal volume of the system of particles. The mass is conserved, or the total volume is conserved rather, and except at this point ti, where in fact the function L of t jumps, this x, which is I guess I didn't write that x is the vector, the sequence xi. This x satisfies this system of ordinary differential equation. And in fact, there is an additional property in this model which can be viewed somehow as a kind of parabolic feature of that equation is that in fact one can prove that the xj of t are strictly positive. Anyway, so for those who are familiar with the Smolerovsky coagulation equation, you have also the same kind of feature in the Smolerovsky coagulation equation, meaning that even if you start with a compactly supported initial data, after any positive time, the support is extend to plus infinity. So just two remarks. So the first thing is that this equation here is satisfied on so if L of t is equal to I, this equation is satisfied simply only on the time interval ti minus 1 ti, but in fact it can be continued up to t plus infinity, but of course the time ti here corresponds at the first instant of time where xi of t reaches 0, and so and then after in the evolution can continue, but with a negative if component. So that's the first remark. This assumption here that the delta I was positive, so I just recall that the delta I was the infimum of the coagulation kernel. The fact that the delta I is positive guarantees that in fact the solution to this vanishes in a finite time, and so that somehow we jump to the next size. And as usual for this kind of equation, the total volume conservation follows from the control of a generalized moment. And what is mainly open at this point is, well, somehow what is the value of this t infinity, which is the maximal evolution to which the system can go. And note in particular that if it happens that t infinity is finite, this means that L of t, the minimal volume, will blow up in finite time. So it means that the distribution, the minimal size is going to be infinity in finite time. So before coming back to the question of T infinity, whether it is finite or not, let me say a few words about the convergence of a stochastic process towards the deterministic limit. So I take again the same deterministic initial condition. Then I take a random initial condition. So now here these x, I, m in are integers. And the constraint is that the total volume is equal to m, and then I rescale this initial data, and I ask that my rescaled initial data or random initial data are close to the deterministic initial data in this sense. And then I assume a little bit more on the coagulation kernel, meaning that I assume that the kij's are bounded, if I here is fixed, the kij are bounded by a constant, but which might depend on I. And that these ki, they do not increase faster than I at infinity. So under this condition, of course, these conditions are stronger than the condition I had for the well-posedness. So on this condition, there is a solution to the deterministic model starting from this initial data. And then one can prove is that somehow this property here is going to be still true in some maybe weaker sense during time evolution. So more precisely, if I call x the solution to the deterministic model starting from x initial, I take x capital M, the Markov process, starting from my random initial data here, and I call t infinity the maximal existence time of my deterministic solution. Then for all t which is smaller than t infinity, I can find three constants, c of t, d of t, and m of t, such that I can estimate the difference of the renormalized Markov process to the deterministic problem and show that somehow what I had assumed at the very beginning is still true for all times, replacing the constant 1 here by appropriate smaller or bigger constant, and provided my capital M is sufficiently large. So somehow this is a kind of error estimate between the random evolution and the deterministic evolution. And a few words is that, in fact, in order to show this, we somehow rely a lot on the approach by Darling and Norris, which was used to show the convergence of finite dimensional random Markov process to a finite dimensional system of ordinary differential equations. The difference we have to cope with here is that in fact the system is not finite dimensional. We have an infinite number of ordinary differential equations, so somehow we have to control some tail here. The fact that the differential system, as already mentioned, changed during the time evolution, and of course, so it changes at each time that that the minimal volume change. But of course, the change of minimal volume is not exactly at the same time for the deterministic model and for the stochastic one. So we have to estimate the difference between the change of the minimal between the time at which the minimal volume changes on the random evolution and on the deterministic evolution. And the remark is that in fact this assumption here was made in order for this nonlinear term here in the evolution of a deterministic system to be Lipschitz continuous, so that one can somehow apply directly the Cauchy-Lipschitz theorem in its basic form. Yeah.
I didn't catch exactly. Do you rescale in the limit, the hydrodynamic limit? Do you rescale the time or?
No, the time is not rescaled. Oh, no,
okay.
no. Only this is rescaled, but not the time. The time is not rescaled.
Because the probabilistic process is discrete time. Is that correct? No, it's not discrete.
It's continuous in time. It jumps only at discrete time, but it's continuous in time.
And for the same time you get this.
For the same time, yes. This is different from Smolrovsky equation, for which you have, if I remember well, rescaling in time. And okay, and to finish with, let me say a bit more about the evolution of the minimal volume. Sorry. So, well, since these are ODE, ordinary differential equations, which are linear, then of course what is very simple first to do is to try to do some numerical computation, and we choose a particular kernel Kij, which is the minimum of phi I, phi j for some given function phi. So phi is going to be either 1, I, square root of I, and logarithm. So here you have in fact this is the curve representing the size and the jump time. So this is, let's say, a function t of I, well, continuous way. So somehow t infinity should be over there. So though here t infinity is t1000. So what one already see here is that if the kernel is 1, then we have a largest value here, and it seems to be still increasing. While if we have kernels which increase more rapidly, it seems that Ti is somehow stabilizing to some value here. So revealing that apparently it's not so likely that that T infinity would be plus infinity in that case, for instance, because it really appears to converge to a constant value. One can also plot the time evolution of the minimal size. So again, of course, the minimal volume is expected to go to plus infinity. But there are different ways of going to plus infinity. So as you see, if the kernel again is constant, then it goes in a, let's say, rather gentle way to plus infinity. While if you take the kernel k of I equal I, the minimal volume seems to increase very rapidly, and somehow you expect a kind of a blow up in finite time here, because somehow this is nearly a straight line here. And the situation again for I to the 1/2 and the log is not very clear on this pictures at least. Still, we can say a little bit more than these numerical simulations, in the sense that one can prove that if Kij is bounded from above by a constant time the minimum of log I plus 1 log j plus 1, then we can guarantee that T infinity is infinite. And somehow we are almost the same, almost opposite result, meaning that if now the kernel is bounded from below by, again, this minimum of log I plus 1 log j plus 1, but to some power which is smaller than 1, bigger than 1, sorry, then this guarantees that the T infinity is finite, and so that the minimal volume becomes finite in finite, becomes infinite, sorry, in finite time. And in fact, this reaction is rather so. This is something which is rather violent, as you have a blow up of a minimal volume, and in fact, what it means compared to the, let's say, well-known Smolorowski equation, it means really that because the minimal volume is plus infinity, that all the particles have infinite size, infinite volume, and compared to Smolorowski equation, this resembles to what is called complete gelation for the Smolorowski coagulation equation, meaning that all the matter which was initially present in your system of particles is transferred to particles of infinite volume. Having this, so having somehow this very nice classification here, of course there is a small gap here which is represented by this alpha. Well, one can wonder whether this deterministic phenomenon here has a counterpart on the stochastic evolution. Well, that's the proof. So, in order to look at this, we will choose, let's say, a smaller class of kernels, and we take phi to be an increasing positive function such that Kij is given by the infimum of phi of 8 and phi of j. In view of the previous result, I mean, this is quite natural because this is exactly somehow what this kind of function that occurs here. So what one can prove in that case is that so you take an initial data now for the stochastic process, and you look at the first time at which somehow you have only one particle left in your distribution. So this is somehow there is no longer no evolution possible afterwards. And what one can prove is that the supremum over all possible initial data of the expectation of this time here is finite if and only if the sum of 1 over I phi of I is finite. So, meaning that, for instance, if you take phi of I to be log of I to the power 1 plus alpha with alpha positive, this criteria is fulfilled. So this guy here is finite, and the corresponding T infinity in here is also finite. So somehow you have let's say you have a trace, or I don't know, a trace of what happens on the deterministic evolution also at the level of the stochastic evolution. The interesting point is that you have really an equivalence here and a very precise criteria which you do not have on the deterministic evolution. But of course the price to be paid is that you have a smaller class of kernels. And the proof, just one word about it, is somehow by a comparison argument, in the sense that you can somehow compare, for instance, so if you take any initial data and you call T1 the first time after which you have no longer particles of size 1, then in fact you can compare this time with the same time, but starting with only with the same number of particles of size 1. And this is also true for this final time. So this, let's say, this comparison first tells you that somehow you have only to work now with this kind of initial data, which is much easier than with, let's say, a generic initial data. The second point is that using this, you can show that the expectation of this time here is bounded independently of the initial data, except of course this one. And an amazing point here is that the proof of this uses the connection of the stochastic process to the deterministic system and the error estimates which we had established in the convergence theorem. And next one uses the fact that when you have chosen this very specific kernel, this minimum of phi of I and phi of j, then somehow you have a kind of rescaling which is in your system, and that somehow computing the time at which, if you start with n particles of size I, and you look at the time, the first time after which all the particles of volume I have disappeared, somehow it's the same as a starting, well, it's the same. It's the same as starting with n elementary particles of size 1, and looking at the time after which they have all disappeared, but you have to rescale it by phi of 1 over phi of I. And then once you have this, then somehow you can prove this kind of identity and then conclude the proof. To finish with, let me just mention a few things which will be needed to be done in the future, near or far future. The first thing, so I restricted myself here to integer valued particles, volume, because somehow the system of ordinary differential here is quite nice, and somehow because since we are in a discrete setting, this minimal volume is piecewise constant. It's not so clear what would happen if x would be a continuous volume variable, because then L of t could be continuous. I mean, maybe possibly could jump. It's unclear, so it's not so clear. I mean, the stochastic process is the same, but its convergence and its deterministic limits are maybe not so clear. The second point is the behavior when t goes to this t infinity. So in that case, for instance, for the model where for this kernel here, this follows from some work by Menon, Pego, and Nitano. And also the next point would be to look at this model, but now with k equal 2, meaning that now when you take one of the minimal particle, you split it into, you break it in two pieces, either equal or different, and you glue these two pieces to two other particles, thus obtaining, well, hopefully a different dynamics. Okay, thanks for your attention.
Well, thank you, Philippe. The comments?
What's the abstraction to transfer this comparison principle you used in the last part to the deterministic model? What's the abstraction? You told me that it's possible to do it on the probabilistic one. So, but I see that you use some probability theory at some point, but is that really impossible to translate it to some extent to the limit?
In that, somehow, I guess in that way, yes. I would say that maybe on this problem, I mean, for Smolorowski coagulation equation, for instance, on some of the stochastic process, you have also, I guess, some comparison. I guess in particular on the for the constant kernel. But then you can recover comparison, but for the indefinite integral of the solution. So there might be a relationship, but it's not. I would say that the dynamics of a stochastic process is more precise, and so you can do more on it than on this, let's say, this average problem.
More comments?
I had another question. In fact, what happens in? Oh, sorry, there was. Oh, sorry. No, please.
No, it's you. It's you, absolutely.
I had another one. I mean, what happens if you have this degeneracy that delta I is 0, you know, in some Smolorowski equation? So, do you know if there are some situations where it's ill-posed or?
It's probably not ill-posed, but what you might have is, so in that case, in what I presented, the minimal volume always jumps +1 each time. If possibly you would have one delta I equal to 0, maybe you could have a jump of +2, for instance, once. And then I guess the analysis for the deterministic problem could be done, but then one has to be more precise at what happens exactly at that point. So that's.
Any more comments?
So the question is, why don't you, in each time interval when you have a linear evolution, why for the calculation you choose a linear mechanism instead of, let's say, having a binary, bilinear? I mean, is there some reason because the original model was like this?
No, there's no particular reason to do. Well, I mean, I guess on the this is related to the choice of the in the stochastic system also, that the you pick one minimum. The rate does not depend on the amount of minimum particles.
Okay, so if there are no more questions, I think